Okay, let me share my desktop. Okay, let's start the presentation here. Greetings. This is a lecture in the Programming in MATLAB for Engineers course at the College of Marin. This particular lecture is on stochastic simulations, or in other words, simulations that involve random events. Over the course of this particular lesson, our objective is first to just understand the basics of how to simulate an individual random event, and then scale that up to a collection of random events. And as we'll see, independent random events. And then we'll spend a little bit of time talking about how one might use that in order to analyze the statistics of the outcomes of those random events. And then we'll talk about how to move from there into simulating random processes, sequential random processes, where we might have multiple events where the outcome of a future event depends on an earlier event. And then finally, putting that all together, understanding how one can take such sequential random processes and use them in order to model a variety of different physical processes that we might encounter as in our world of science and engineering. So first, I just wanted to take a minute to review the basics of how we generate random numbers, something we talked about early in the course, and we've had opportunity to practice a great deal through various homework exercises and such. You'll remember that in order to just generate a random real number, we use the rand function, the built-in rand function in MATLAB. And you'll remember that the input arguments for the rand function are the number of rows and columns of random numbers that you'd like to generate. And those input arguments are optional, so if we just say rand, we'll get one random number. If we give it a number of rows and columns, we'll get an array of random numbers. And you'll remember that those random numbers that we generate by the rand function are real numbers between 0 and 1. And so if we want to get a random number in a range other than between 0 and 1, we of course need to scale that random number appropriately. And so if we wanted a random number in the range of low to high, you'll remember that we need to multiply our random numbers by the difference between high and low, so the size of that range, and then shift the random numbers up to whatever the low value is. So we've had lots of practice using that. And you'll remember that if we want a random integer rather than a random real number, the easiest way to do that is using the built-in function in MATLAB, the randi or randy function. And you'll remember the syntax is a little different on that one. First, we need to give it a vector of two numbers that has the low and the high for the range of integers we want, and then we give it the number of rows and columns of random integers that we'd like. Alternatively, we saw that another approach is to just use the basic rand function and then use floor in order to cut off the decimal portion of those numbers, and that we needed to scale shift by one more in our high minus low, shift upward by an extra 1 in order to have that work out. And in fact, in our lab exercise on these random simulations, you will get to investigate the idea of using that floor and shifting and why that is a preferable way compared to just rounding the random number. And that's one of the exercises that you'll explore. You'll also remember that the rand function does not give true random numbers. They're pseudo-random. That is, they're generated the same way every time that you start MATLAB, and so you get a dependable set of random numbers, if you will, every time you restart MATLAB. And so if you wanted to get a truly random number, then you need to shuffle that rand function, and one simple way to do that is to use the RNG command in MATLAB with the input argument shuffle in quotes, and that will randomly shuffle the rand function so that you get truly random numbers after that, or at least somewhat truly. Okay, and then if you do need to reset the rand function without shutting MATLAB down and restarting it, you can use RNG default to reset it back to the beginning again. And of course, we talked about previously, one of the reasons you might want to do this is during the developing and debugging phase of your simulation program, you might want to use the same random numbers over and over again in order to test whether changes in your programming structure change the outcome. And if you were using truly random numbers, you'd never be quite sure whether the changes you made were due to new random numbers that were different or due to your changes. So this is a way that during the debugging phase, at least, you can get the same set of random numbers every time. Okay, so now that we've reminded ourselves of how to generate a random number, let's talk about how one uses that to simulate a random event. And the basic concept is pretty straightforward. First, you need to declare some probability level for the event. And that's a probability in decimal form. So if it's a 50% probability the event's going to happen, you would say that p equals 0.5. If it's a 75% probability, you'd say p equals 0.75, and so forth and so on. So for example, for flipping a coin, the probability of a head is 0.5. Then the next thing we want to do is generate a random number. And for this particular example, we're talking about generating a real random number between 0 and 1. And then we just want to compare the random number that we generated, which we've stored in the variable r, to the probability level that we specified, p. And if r is less than p, then we'll consider that to be the event occurred at the probability we specified. And of course, because we have evenly distributed random numbers between 0 and 1, the random number r that's generated will be less than p about p% of the time. And we can verify this in a moment with an example. And of course, if r is less than p, then there's some event that takes place, and we, of course, will program whatever actual computer actions we'd like to take place associated with that event. And then, of course, often we want to know what happens if the event does not happen. There's often an alternate event. Of course, if you're flipping a coin, if r is less than p, we'd say that we got a heads. Otherwise, of course, we got tails. So if it's a dichotomous outcome, one thing or the other, then you would typically have this structure. If r is less than p, the event happens, else the alternate event happens. So let's take that concept and extend it a bit by looking at an example. And so this example is going to run throughout this lesson. And this is the example of bacterial growth, which we've seen in a previous lesson. So the concept here is that we're going to simulate a colony of bacteria that are growing. And bacteria reproduce through asexual reproduction. That is, they split in half and divide. And so in each generation, we'll call it, of bacteria, and we'll assume that they're all synchronized for the purpose of this example, even though that might not actually be the case. But we'll assume that they're all synchronized so that there's a generation of bacteria and subsequent generation and so forth. And in each generation, any individual bacterium that's in the colony will either divide, in which case it produces 2 identical offspring, or alternatively, it will die and disappear from the population. And so we're going to utilize that assumption throughout this entire example as we expand this up to more and more complex simulation. Okay, so let's actually leave PowerPoint and go into MATLAB for a moment. And we'll go into the editor window here and play around a little bit with the idea that we talked about. So first we'll just start out with a simple script. I'll call it divide, that will simulate cell division for a single bacterium. And so first we need to specify a probability level, as we said before. And so let's say that the probability of a bacterium reproducing any individual one is 0.75. So in other words, there's a 75% chance of reproducing, or a 25% chance that it will die. Next, we need to generate a random number associated with that cell division and store it in some variable r. And then, as we said earlier, if r is less than p, and here, in essence, we're deciding whether or not there was a successful division or whether it died. And if it was successful, we'll just display divides. Otherwise, it dies. And that's really it in terms of just simulating one particular event. And so I'll save that and run it. And so if we run this the first time, we see that it divides. I can run it again, divides, divides. And we can keep running it over and over again. And we're getting a lot of divides. And finally, after quite a few times running this, we finally get dies. And of course, one of the nature of random numbers is that it doesn't necessarily do it in a systematic way. That is, you don't get 3 divides and then a die, even though overall you would expect that 3/4 of the time you get a divide and 1/4 of the time you get a die. But of course, it's random, and so it can occur in various ways. So one of the things that we might actually be interested in doing is analyzing whether, in fact, we are going to get divide about 3/4 of the time and die about 1/4 of the time. And in order to do that, we'd need to run this program over and over again many times and then analyze the results. And of course, since we have a computer at our fingertips, an easy way to run something over and over again is to use a loop. And so we can do that here. Now, if we are going to have a loop, we need to specify how many times we're going to run this loop. And since eventually we're using this to simulate a colony of bacteria, we're going to simulate this event for every single member of the bacterial colony. And so what we really want to specify is some population size. So let's start out with just a population of 20. And so that will correspond to our current population of the bacteria. Right? And then If we wanted to, we could now generate a loop that goes through every member of that population. And so I need some counter variable. I'll use bactnum for the bacteria number. And it's going to go from 1 up to the population size. And then we are going to simulate this event for every single one of the bacteria in the population. And one of the things that I should emphasize here, do my Control-I to space that out, is you'll notice that I've put the random number generation inside the loop and not outside the loop. And of course, that's important because we want to generate a new random number for every single one of the bacteria. That is, it's a new independent event. So for each individual member of the population, they may live or they may die, depending on their own randomly generated number. The probability, however, for them living or dying is the same. That is the value p that we've specified earlier. So we can specify the probability level at the beginning outside the loop, but we need to generate a new random number for every single event inside the loop. And so now we can do this over and over again. And of course, if we do that and run it, I'll go out here and clear the command window. We can see a whole string of divides and dies. And so we can scan through, but of course that may not be an efficient way to figure out whether we have 3/4 or not. It would be more efficient to actually count them. And of course we can do that by replacing our display statement with some kind of mathematical expression that simply counts how many divides and how many dies. And for that, we need a variable. So I'll use live for when the bacteria successfully divides. And I'll use die for the occasions where the bacteria dies rather than dividing. And so now we're counting the number of divisions and the number of deaths as we go through the loop. But we can't, of course, count them and use those variables unless we have first initialized them. So before the loop, we'll need to initialize both of those totals to be 0. Okay. And then, of course, once we're done, we'd like to know what the results are. So we might want to output, for example, using an fprintf statement, out of however many bacteria we're simulating, how many divided? And we'll put a new line afterwards. And so we can therefore indicate with our fprintf statement how many bacteria we simulated with our loop, and out of that number of bacteria, how many divided, or in other words, lived. And we might also want to express that as a percentage just so we can compare it to the 0.75. And so maybe we'll put a second fprintf statement, and I'll call it the reproduction rate. And I'll just display that to 2 decimal places. And here we just want the ratio of the number that lived to the total population. And so now we can go back and we can run this program again. And we're told that, oops, I forgot to put a %d in my format code there. So out of 20 bacteria, 12 divided, which is a reproduction rate of 0.6. And I can run that again, and I see that the second time I got a slightly different result, 0.8, and so forth and so on. And I see get slightly different numbers every time. That range so far from 0.6 to 0.8. And of course, because it's random generation, that ratio will fluctuate somewhat. Now, of course, the larger the number of events I simulate, the closer I will get to the actual percentage. And so to verify that that is true, we can just go to our program and increase the population size. So I'll bump up the population to 200 bacteria, and we can go back and try this again. And we get 0.74, 0.79, 0.75, 0.72, 0.72, 0.75, 0.76, and we can see that we're much closer now to the theoretical 0.75 each time. And of course, if we were to go in and bump that number up to 2,000 rather than 200 and run it again, now we would get very close to 0.75 every time. You'll notice with these repeated runs that we're basically plus or minus 0.01 from the theoretical value of 0.75. And that's a general statement about simulating random events, is that if we have some probability level, that probability level should be approached as the number of events goes towards infinity. So as we have a very large number of events simulated at that probability level, our outcomes will tend to approach that. And so to reinforce that idea, so there was our simulation. We talked essentially there and showed an example of collections of random events. And again, to reinforce, if events are independent of each other, we need to generate a new rand for each event that takes place. And that the percentage of successful events will approach p as the number of events approaches infinity. Now, in order to do this sort of statistical analysis on outcomes, it's often useful, and we can be more efficient in MATLAB, rather than using a loop structure, we could use a vectorized approach, and I'll demonstrate that in a moment, in order to generate a lot of random numbers at once, rather than one at a time, and then to simply evaluate the outcomes of those random events. And one efficient way to sort of keep track of the statistics and view the statistics of the outcomes is using a histogram, otherwise known as a frequency distribution. And you'll remember that's simply a count of how many of the results are within a particular range. How many are between 0 and 1, how many between 1 and 2, and so forth and so on for some outcome. And so there's a built-in hist function in MATLAB, and it has various options on how you call that function. The simplest is to simply call hist with a vector. So you give it some variable that contains an array of values, and it will generate a histogram of those values by counting how many fall in particular ranges, which are typically known as bins. And if you don't specify the bins, MATLAB by default will use 10 equally spaced bins. So if your values can fall between 0 and 1, then it will simply go through and separate the range into 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3, and so forth to get 10 equally spaced bins, and then count how many fall in each of those ranges. However, if you would prefer different bins than the default 10 bins that MATLAB specifies, you can do so with a second optional input argument, where here binvec is just some vector that specifies what the bin values are going to be. So if I just wanted 2 bins, I might say 0, 0.5, and 1, or 0.5 and 1, whatever the case may be, to specify what those bin values are going to be. And then finally, I should note that in both of the cases above, where we just call the hist function, MATLAB will generate a plot, that is a histogram plot of the outcome. If rather than a graph, what we'd like to do is simply capture those counts and store them numerically, we can do that by simply providing an output argument and assigning the result of the hist function to a variable, which I've called counts here. And that will assign the resulting counts to this variable, and we can use those counts for other types of calculations. So let's go back to our bacterial example in MATLAB and demonstrate how one might do this. So first, I had mentioned before that we can actually, I'm going to save this as a new program. I'll call it divide 2. That here will be a vectorized approach to simulating this event. And here I mentioned the idea that rather than using a loop and an if statement, we can replace that loop and if statement by generating first a random number, or an array of random numbers. So R can be a vector rather than an individual random number. And of course, we simply specify one row and how many columns of random numbers we'd like. And we notice from our loop below that the number of random numbers we'll need is just the population size. And so whatever the population size may be, we need that many random numbers. And I'm going to bump that back to 20, by the way. And then what we'd like to know is how many lives and dies, if you will, did we get. But we'll start out by just looking at what are the array of random numbers, looking at a histogram of the array of random numbers that are generated. So we can just simply do hist of R in order to be able to visualize what these random numbers look like. And so I'm going to get rid of all my earlier output and the loop, and essentially here just with R equals random1 comma pop, we're simulating all these events, although we haven't at this point decided how many live or die. We can run this and generate, as I mentioned, a histogram of the results, and we see here that we have a variety of bins that go from 0.1 up to 1. So MATLAB by default has decided to create 10 bins and to count how many appeared within each bin when it generated those random numbers. So out of the 20 random numbers generated, we can see that the counts vary from 0 in some cases up to 3 in other cases, often 2. And of course, they're not evenly distributed. And that's because we've only generated 20 random numbers. If instead we were to bump that number up to 200 and repeat, we would expect it to be more uniformly distributed, which it is. And so now, out of the 200, we see that on average, they tend to be around 20, but still fluctuate somewhat, but not as much as previously. If we were to bump that up to 2,000, it would tend to get even more uniform, approaching that 10% for each bin, 200, and then 20,000, even closer. And of course, as we mentioned previously, the larger the size of your collection of independent events, the closer you will be to approaching the probability level that you expect. In this case, because the random numbers are evenly distributed, we expect the values to be between 0 and 0.1 just as often as they are between 0.9 and 1. That is, they should be about 10% of the time for each of these bins. And in fact, that's what we're approaching as we increase the sample size. Now, I mentioned previously that one of the things we might be interested in is not really looking at the actual random numbers generated, but rather how many times the bacteria lives or dies. So in that case, what we really want to do is just simply test, is R less than P for each one of the random numbers? And of course, we know that in MATLAB, when R is an array, and we apply this relational operator, less than P, we will get an array of trues and falses. That is a logical vector. And so what we're really plotting here is a histogram of the outcome of that logical array, which will have some number of trues and some number of falses in it. And so I'll go back to a population size of 20 and run this again. And now when we look at the histogram that comes out, we see, of course, that there are only 2 bars. And it doesn't really matter whether I do it with a population of 20 or 200. We will still only get 2 bars, and that's because the only possible outcome here is 0, which is false, or 1, which is true. And so there's only 2 bins we can get. So in that case, it doesn't make much sense to have MATLAB dividing this x-axis up into 10 equally spaced bins. We should really just have 2 bins, one for true and one for false. And we can do that in MATLAB in the hist function by specifying that second input argument, and that is to tell it using an array what bins we would like. And so here we'll give it the array 0 and 1. And so rather than getting a bunch of empty bins in the middle, now when we run it, we'll simply get 2 bins, 1 bin for the zeros and 1 bin for the ones. And we can see that out of our 200, we got slightly more than 40 for the dies and close to 160 for the lives, which is slightly off from what we expect. But of course, as we bump that up to a larger population size, we get closer and closer to the expected result. So here with 2,000, we get 500 dies, and of course 500 out of 2,000 is 1/4. And 1,500 out of 2,000 is 3/4, or in other words 0.75, the probability level that we expected. And I mentioned previously that often what we might like to do is not to display a graph of the result, but to actually capture those numbers. And we can do that by taking the histogram function and assigning the output to a variable, which I'll call counts here. And so in this case, if I run the program, instead of getting a plot output, I can go to the command window and type counts and see that in fact I now have captured the 2 counts, 494 that died and 1,506 that lived. Very close, but not exactly equal to the 1/4 and 3/4 that we expected. Okay. So let's go back. So now that we understand how to model random events and large collections of independent random events, the next thing to talk about is random processes. So here what we're talking about is a sequence of events that are not independent of each other. Or in other words, what we mean by that is that the result of one random event will influence how we proceed in simulating the next random event. And so we can't do them all at once. We have to do them one step at a time in order to see what the outcome will be. And there are many examples of this, and you'll explore a few in your lab exercises. But one simple one that we'll look at here is to continue with this bacteria colony example. And in this case, what we're going to do is, rather than just simulating one division or one generation for this colony, we're going to simulate multiple generations of the bacterial colony. Now, at each generation, we can use the program that we've already created in order to simulate division for each individual in the population. So whether we do that using a loop, or whether we do that using the vectorized approach that we saw more recently, in either case, we can simulate that division for each individual and decide whether each lives or dies. And as a result of those divisions, we can then update the population to reflect how many bacteria successfully reproduced. And of course, if that happens, you'll remember that one bacteria becomes 2. And if they die, that one individual becomes 0 or disappears from the population. Another way of thinking about that is that when the bacteria successfully divides, the population goes up by 1. And when the bacteria does not successfully divide and dies, the population goes down by 1. So really all we have to do then is figure out how many individuals in the population successfully divided and increase the population by 1 for each of them, and then figure out how many individuals died and decrease the population by 1 for each of them. And that will conclude simulating one generation of divisions, and then we can repeat that process for multiple generations. And of course, when we go to the second generation, we'll have to know how many survived and died through the first generation. That is, we need to know what the new population is in order to simulate the next generation, and so forth and so on moving forward. And then we can track the progress of our population over time and see what happens. So let's go see how we might implement that. So one of the first things that we're going to want to do here, I'm going to pull back up our simple version with the loop that we had previously. Okay, MATLAB's not cooperating at the moment. Oh, there it goes. Okay. So here we have that earlier version, and I'll just start with that simple one, but we're going to modify it slightly here. And the idea is that we are going to be simulating this generation of divisions over and over again. So it makes sense at this point, in order to have this portion of the script really be in a function rather than being a separate program. So we'll create a new function, which I will call BactDiv for bacteria division. And in order to simulate the division for a whole colony of bacteria, I need to know what is the current population, and I'll call this last pop. So what is the current or previous population before we started this division cycle? And then I'll also make the probability level an input argument so that it provides some flexibility in modeling this bacterial division. And then we need to assign the result to some output argument, and I'll make it a different variable name than the input. So we'll input a previous population and output the next population after we've simulated cell division. So we're going to simulate cell division for one generation of bacteria colony. And inside, we no longer need to specify the probability level because that's now coming in as an input argument, so we can get rid of that. And similarly, we don't need to specify the population anymore because that's coming in as an input argument. And we're not going to count how many live and die inside the function. We'll do that wherever we're calling the function from. And so really then we're down to the basics of this program, which is for some index variable, which I'll leave back num, going from 1 to whatever the population is, except in this case, we recognize that here we want to use the entering population that was inputted, which we call last pop. And for each one of those, we want to generate a random number. If that random number is less than p, we want to increase the value of the population. So pop equals pop plus 1. And as we mentioned, for each time that was unsuccessful and a bacteria dies, we want to decrease the population by 1. And of course, here I'm using a variable pop that doesn't exist yet, so I need to initialize that variable up above to start out being the same as last pop. And so here, we come in with whatever the previous population was. We temporarily store that in our output argument pop. And then we run through all of the individuals in that original population, changing the population up or down by 1 at each cycle for each bacterium to see what our final population will be. And we no longer need any output because this is in fact a function, and the output argument pop will be passed back to whatever program called it. One of the things I should emphasize here is how important it is that we did not use the same variable here for the index of the loop as we used here for keeping track of the increasing or decreasing population. The problem would be if we had had the loop go from 1 to pop, pop changes during the course of the loop, and so the final index of that array would change over the course of the run of the loop. And so that's why we need 2 different distinct variables here in order to keep track of this. And of course, since I've now made this a function, I need to do save as and call this bactdiv so that the name of the file is the same as the function name that we're using simulated. And so now we can pull up the command window, and we can clear our variables, and we can try testing this function to make sure it works. So first I'll just call it using the name of the function, and we need to give it its input arguments. So last pop, let's make it small. So let's say there are 5. And let's say that the probability level is 0.75, as we've done previously. And we get that the output argument is 8. That is, we get back a population that's different than what we sent in. And of course, we can bump that up to 20. And we see, if we repeat this, let's do it a couple of times with 20. that we get a different result each time. And we'll also notice that the population coming out is larger than the population going in. And it's important to recognize here that here we're not capturing how many divisions we had or how many deaths we had, but rather what we're just keeping track of is the fluctuation in the population itself. Does it go up or does it go down? And so the output argument we're getting here is in fact the final population after all of the bacteria individuals have had a chance to either divide or die. Now in order to simulate multiple generations, which was our goal previously, then we need to create a new script or function that's going to call this function. And because we're going to, after this, scale this up one step further, I'm going to make this a function rather than a script. And so I am going to call this function BactSim for bacteria simulation. And again, what we want to do here is have some output argument, pop, that is going to have the population of the bacterial colony when we're done simulating multiple generations, except in this case, our pop is going to be a vector at each generation rather than, and maybe we should change the name and call it popvec just to make that clear. It's going to be an array of populations at each generation that we simulated. And so as inputs for this simulation, again, we'll make P the probability level in input, and also the number of generations that we want to simulate. So we'll call that NGen. And so we'll just type a comment here to make it clear what this is doing. And so in this particular program, we're going to start every time with a single bacterium. So starting with a single bacterium, during each generation, current bacteria divide with probability P or die. And that's essentially what we're simulating. And so we're going to do this for multiple generations. And so first, we need to start out by specifying how long we want to continue doing this. And of course, we're going to do it up to the number of generations. So we could do this for some generation number, which I'll call gennum, is equal to 1 to NGen. We can call our function BactDiv, and we're going to call it, of course, with the current value of the population. And the current value will say will be gennum minus 1. And in fact here, if we're going to do it that way, we want to go from gennum equals 2 to NGen. And of course we need to specify the probability P that goes along with that. And then we need to assign that output to the new value of the population, which will be pop of gennum. And again, this is an iterative procedure that we're doing here. where each time we go through the loop, we take the current population, which I'm calling gennum minus 1. We're calling our division function in order to figure out how many live and how many die and update the population. The output of that will be some scalar value, pop, and excuse me, I forgot to make these all pop vec. The output of that will be a scalar, which will then assign back to the array popvec, but this time we'll assign it to the next element of popvec, which will be gennum. And of course, one of the things this requires is that we initialize the first element of the population vector, popvec of 1, to be whatever we want the starting value of the population to be. And again, we said, for the purposes of this example, I'm going to start every one of the populations. Every time I run the simulation, I'm going to start with a population of 1 bacteria. And of course, we know from previous examples we've done that we can be much more efficient in MATLAB if we're using an array like this and indexing. If we initialize the entire array, if we pre-allocate it in advance, and so we can do that by using the zeros function. And so if we're going to simulate NGen, number of generations, we can just pre-allocate popvec to be that number of zeros. And then we will fill that population vector as we go along. Again, the first element we'll set to 1, and then we'll step through from the second element up to the last one, which will be NGen, since that's an integer number. And then we'll go through each time, and we'll take the previous value, the first time through, that will be 2 minus 1, so popvec of 1, which is our initial population. And then we'll get from that the second element of popvec, or for the second generation, and so forth and so on. And then when we're done with this, we should have a vector output argument, popvec, that contains the populations at every generation. And now, of course, we need to save this as bacsim.m. And we can go to the command window and clear and run this. So we can say bacsim of 0.75 for the probability level, and then the number of generations, and let's just do it for 5 generations to start with. Keep it small. And when we simulate it, we see here that we get 1, 2, 2, 4, 6. So as expected, the population started out with 1 bacterium, and then it increased over time. And we can see clearly that in some cases, so in this first case, clearly it successfully divided to 2. The next time around, obviously one of those bacteria died and the other one divided, so the population stayed stable at 2. The next time both successfully divided, we went to 4. And then, of course, then we had to run it for 4 of them, and it grows over time. Now, if we run that simulation repeatedly, because it's a random simulation, we're going to get different events. Right? And one of the things we might want to do now is to scale that up to a larger number. So we might want to run it for, say, 20 generations. But if we do, we don't want to necessarily just let it randomly print out on the screen. And so I am going to use an output argument to capture the vector. So I'll just call it popvec again. is going to be equal to backsim of 0.7520. And then if I want to see it, I can display it using transpose, and it'll be a little cleaner on the screen. And I can repeat this process over and over again. And one thing I might be curious about is what happens if I were to change the probability level. So what if the probability were only 0.65? And we see here that with a lower probability level, we seem to have a lower probability of successful division. And one interesting thing is, something I was trying to get to happen on the other one, if the first bacterium dies, does not successfully divide, there are 0 left in the population, and yet MATLAB continues to simulate for n generations, even though that's not a particularly efficient thing to do. So we really could get a little smarter in our loop and stop the simulation for the colony when we drop to a population of 0, because at that point, obviously, it's going to stay 0. We're not going to get any more individuals in the population. So how would we do that? Well, of course, we could do that using a while loop rather than a for loop. So we could go back and replace our for loop with a while loop, where one of the conditions will continue to have to do with the generation number. But in this case, what we're interested in is whether gennum is less than ngen or not. And so once gennum reaches ngen, we should stop. But of course, in order to keep track of that in a while loop, we need to explicitly count gennum, which means we need to first initialize it to some value. So we'll initialize it to 1 for the first generation. And then within the loop, we're going to need to explicitly increment gennum. So now we can count the generations, so starting at 1 and then incrementing each time. And let's say we were going to do 2 generations. If ngen was 2, then the first time we'd enter the loop, we'll come in and 1 will be less than 2. And then we're going to increment gennum to 2. And then you'll notice in our calculation here, we're taking gennum minus 1. Since we just incremented, 2 minus 1 is now 1. So we're taking the first value of popvec and using it to calculate the second value of popvec. And at this point, we're done. And so we would only go through the loop once. And you'll notice that's because in this array, our first element and what we're calling our first generation is really the initial value. So our first generation is our starting point. And of course, if we had more than 2 generations, this would simulate it, and we'd get a new population for each generation after the first one. But of course, the reason for switching to a while loop was so that we could add an additional condition to make this a little smarter, which is that we only want to continue the simulation as long as the current population that we just calculated is greater than 0. So while the population of gen num is greater than 0, and while gen num is less than NGen, we can continue this simulation. And it will stop whenever the population drops to 0. And we won't continue. And since we've already pre-allocated popvec to be zeros, all of the remaining elements will be zeros by default. And of course, MATLAB is reminding us here that we would be more efficient if we use the double and, since those are going to be scalars. So let's clear CLC. And we'll run our simulation again. And as usual, I've done this several times. I keep wanting to call that pop, and it's actually popvec. So again, good example of debugging if you read the error. So I went in and adjusted my condition for the while loop to be popvec rather than pop. So let's rerun that. And then we can now display the results. And now when we run our popvec and all of the bacteria die at some point, we know that the loop will quit. If we wanted to confirm that, by the way, we could always, inside of our function, have some flag that tell us when that occurs. So we could, for example, have an if statement here. If gen num is less than NGen, display extinction. The entire population died. So of course, if we made it all the way through for all of the generations, then the last time through, gen num will be incremented and be equal to NGen, which kicks it out of the loop. So if gen num is less than NGen, it's because the loop ended early due to the population vector going to 0. And so we can run that again. And we see that the first time through, we got extinction. And we can confirm that by displaying the population vector and see that, in fact, that was true. If I do this a couple of times, eventually I'll get one where they did not go extinct. And we can see here that we got a population that continued to grow and did not become extinct, and we did not get the flag extinction. So we can verify that, in fact, it is working as expected. Okay, so now let's go back for the final portion of this. Now to take this one step further, we now understand how to model independent events, collections of independent events, and now processes that are no longer independent but build upon each other. And you can put all of this together in order to model various physical processes. And of course, in your lab exercises, you'll look at one specific example that has to do with heat conduction. And it turns out that many different transport processes, conduction of heat, diffusion of mass, electrical charge, and so forth, can be modeled by a stochastic random walk process. And of course, there's lots of other processes that people model using random events in, for example, the financial world and things like that. And one of the things that's interesting is that often when we represent these physical phenomena using this sort of random simulation, we can predict what the average outcome will be as long as we have a large enough number of simulations. So we saw the example of this in the lesson where if we increase the sample size large enough, we started to approach what the expectations were, that is, the probability levels. And of course, even for fairly complicated processes, it's possible to do statistical analysis to see what you would expect the result to be as n goes to infinity. But that's not always the case. However, there are plenty of examples where we can demonstrate that you can use either a stochastic, statistically based model, or a deterministic, that is, a differential equation or continuous type model, in order to describe the same physical phenomena. And so you'll look at an example of that in diffusion or in heat transport, where you'll look at the idea of using sort of these continuous differential equation models that one might use to describe heat conduction. That is, heat flows in proportion to a temperature gradient. Or you can use a statistical model, a stochastic model, where heat conduction is envisioned as the random walk, if you will, of vibrational waves through a material, is another way to look at heat conduction, and they both give the same result under the right conditions. And we can look at an example of it here with bacterial growth. In fact, in an earlier lecture, we looked at a deterministic model of population growth over time for a bacterial colony. And you'll remember it was the example we used for solving a first-order ODE, ordinary differential equation. And it looked like this one, dn dt equals Rn, where you'll remember the lowercase letter r was the growth rate, or the average number of offspring per individual per unit time, and n was the population size. And so this is a deterministic or continuous model of how you would expect population n to depend on time t for some given parameter r that describes the growth rate of the population. And you may also remember that we can solve that differential equation fairly easily using calculus by separating variables and integrating, and that we got an exact solution for that differential equation that was exponential, which is why this is often known as exponential growth. And so n was equal to n naught, which was the initial population, times e to the RT, where again r is this growth rate and t is time. So one of the things I want to demonstrate here with our bacterial growth model is that we can get exactly the same result with our stochastic model, our statistical simulation, that we did with our deterministic model. That is, we can get the same result, n equals n naught e to the RT, as long as we use a large enough sample when we model our bacterial colonies. Now in this case, we notice that for any individual bacterial colony, we have the problem, we have the problem that at any given time, at any given simulation, the bacterial colony could become extinct. And so in order to get accurate results to compare to the deterministic model, what we'll actually need to do is simulate this bacterial growth for a bunch of different colonies and then look at the statistics of the result. Or in other words, we'd expect the average for a large number of simulations to match this mathematical equation that we have from our deterministic model. One of the things you run into, however, whenever you're trying to match up a deterministic model with a stochastic one, is that you need to do what one might call dimensionalizing the stochastic parameters. So for example, in our statistical model, we talk about generation numbers. That is, we're talking about the first generation, the second generation, the third generation, and so on. But in our deterministic model, we don't have anything to represent generation numbers. Rather, we have time. And of course, those two things are related. If we assume that the bacteria have some regular division time where every so often they're all going to divide at once or die, and then we know what the generation number is, we can then figure out what time is. And so down below here, we can write some equation that says, well, if we know what the generation time is for each cycle of cell division, then we can simply multiply that by gen num minus 1, and it will give us the time that appears in our deterministic model. And of course, the reason we have gen num minus 1 here is because the first generation is our starting population, and so 1 minus 1 is 0. In other words, initial time, or time equals 0, corresponds to our first generation that we start with, and so our second generation is created t-gen later, and so forth and so on for later generations. But we also need some way to tie the probability level p to this growth rate r. And one of the problems you'll notice is that p is just a probability level with no units, whereas r, the growth rate, is the number of offspring per individual per unit time. So r has time in the denominator, while p does not. And you can do some fancy mathematics to demonstrate that the relationship is given by the equation at the lower left, which is that r is equal to log of 2 times p divided by that generation time, t-gen. And of course, this gives us that time unit in the denominator. And the log 2p requires a fancier statistical mathematical argument that I don't have time to do here, but you can take my word for it, and we'll try to prove it momentarily by comparing the two results. For the purposes of our demonstration, we'll need some value for t-gen. And so, for typical bacteria, a reasonable number might be maybe about 20 minutes for how long it takes each bacteria on average to divide. And since we may want to do this in hours, that would of course be about 1/3 of an hour. So we'll use 1/3 of an hour for our generation time for the simulation. And of course, we're going to specify some level of p for the probability. And from that, we can then calculate what the corresponding value of r would be to plug in to our deterministic model in order to compare the results. So let's go take a look at that. Okay, so we need to go back, and I've already prepared some pseudocode for this program, and we have a description here that the program is going to analyze bacterial growth from multiple simulations. And again, as we said previously, we're going to start with a single bacterium in each colony. During each generation, it's going to divide with probability p, or die. And if all of the bacteria in the population die, there's extinction, and we end up with a 0 population. So in order to model this, first we have to decide how many generations we're going to simulate in each one of these simulations. So let's say that n-gen is going to be 20 here. And that's somewhat arbitrary. We need to specify a probability level that we're going to use for this study, and we'll just use 0.75 since we've been using that frequently before. We need to specify how many simulations we would like to run, and of course we showed previously that the more we use, the more reliable our results will be, but we can start out with, let's say, 10, and then we'll scale it up. we need to initialize some variable that we're going to use to keep track of the average population vector from each simulation. So you'll remember each time we run this, we get popvec, an array of populations for different generations. But what we want to do now is to average all of them over multiple simulations and look at the average population vector. And so I'm going to call that average pop. And we'd like to pre-allocate that to be the same size as popvec, which of course is just 1 to NGen, our number of generations. And so now we are going to create a loop for the simulations. So for n equals 1 to n sim. So for each simulation, we will call the bacteria simulation function, which is bacsim, with the probability level and the number of generations that we want to simulate. And then we'll assign the result to some output. And I'll call that popvec as previously. So each time we'll get back a population vector for each generation. And then we want to take that population vector and we want to add it to our average pop vector. And so in reality, it's a running sum at first until later we divide by the total. So after our loop, we'll then take average pop and we'll divide average pop by the number of simulations. Since we basically just summed now all the population vectors, so if we divide by the total, that will give us the average pop at each generation. And then we can create a plot now of what that population size looks like for each generation. So we can plot NGen, average pop. And I just noticed that I did the same thing I had been doing previously, which is forgetting that that was called popvec. I think I'm covered there. And then we'll just throw a quick title on there, pop growth. And we need to label our axes, time in hours. And population. And now we can test this out and run it to see what happens. And this time we'll notice that we got extinction here. And let's see what's going on. Okay, we do have 20. Oh, excuse me, I put plot of NGen, average pop, but here I meant to put 1 colon NGen. That is to create a vector from 1 up to the last generation. So in other words, for each generation. And now if we look at our plot, there we go, we will see an actual plot of population versus generation number. And at this point, it's not really time in hours because we haven't scaled this yet properly. So it's really generation number. So what I wanted to do at this point was really then to compare the result of this simulation to the actual dimensionalized version. So what we need to do is go back and calculate the deterministic version . And so we need to specify, as we mentioned earlier, some generation time, which will make 1/3 of an hour. And then we can calculate the time from that. And you'll remember that we said we just take tgen and multiply by our generation number minus 1. And so that means we're going to go, we need an array that goes from 1 to n-gen. And then we need to subtract 1 from that. Or in other words, if we subtract 1 from 1, we get 0. And then n-gen minus 1. And so now we have an array that goes from 0 to n-gen minus 1. So that will be our generation numbers minus 1 at each generation. And then we multiply that by tgen in order to now generate an actual vector of times. And then we said that r, that parameter that appears in the deterministic model, is just the log of 2p divided by tgen. And then finally we can calculate the exact population according to our deterministic model as the exponential of RT. And technically it's n0 times e to the RT, but we're starting with a starting population of 1 every single time. So I'll just put a 1 in there. And then finally, now we can create a true plot of population versus time, where now we're going to plot both of them together. So rather than having 1 to n-gen, we're actually going to plot time, the average population, and then we'll repeat that for our exact population, and maybe we will use symbols for our stochastic result for average pop, and we'll use a curve for the exact values. And then in addition to our title here, we might want to put a legend, to separate the stochastic from the deterministic results. And now we can go back and clear our variables in the command window and see if our model works. And again, as a reminder, what we're doing is going through for each simulation, we're calling the bacterial simulation function, which will simulate a number of generations. Within each one, the bacteria simulation function is calling the bacteria division function with the current population, which you'll remember is simulating each individual generation for all of the individuals, passing that back to the bacsim function, which then is passing that back to our overall control program here that's running a number of simulations and analyzing the results. And so if we run this, we see that we had several extinctions there, and we get some result in our plot that when we average seems fairly close to our deterministic model. And of course, if we bump up the number of simulations that we're running, we would expect, as we see, that the stochastic results get closer and closer to the expected deterministic result. And so that is, as you can see, an example of how one can take what starts out as a relatively simple simulation of a random event and build that up layer upon layer to collections of events that eventually depend upon each other to form a process, to simulate large numbers of those processes taking place, calculate statistics on the result, and use those averages and other statistical measures in order to infer actual physical results that might otherwise be described using differential equations and solutions to differential equations. And of course, you'll get an example to do something along these lines in your labs that involve simulating heat conduction using a stochastic process.